Hello everyone, thanks for attending my presentation. I'm Jaewon from Sungkyunkwan University. Today I'm going to talk about Libpubl, exploiting persistent user buffers as logs for write atomicity. By using non-volatile memory as the main memory, NVMe systems provide many optimization opportunities in file systems. Numerous NVMe-aware file systems exploit the performance of NVMe in their own ways. But they all need their own recovery mechanism to guarantee write atomicity in case of system failure. To improve the performance, library file system runs on POSIX file system and uses memory mapped I/O. But memory mapped I/O does not guarantee write atomicity. So we should provide a recovery mechanism to support write atomicity. Copy on write and logging are main techniques to guarantee write atomicity. However, copy on write causes a severe write amplification when the data is not page aligned or not the multiple of the page size. Logging also incurs the overhead by writing all updates twice, once to the log and once again to the file. We want to avoid this copy overhead by using persistent user buffers as logs. Let's see the design of Libpubl. Libpubl aims to minimize the write amplification. It exploits persistent user buffers as logs. By allocating user buffers in non-volatile memory regions, it can manage them as logs in a sophisticated manner. While previous logging systems intrinsically suffer from the copy overhead, Libpubl can perform logging without additional write to the log. This is the main idea for Libpubl. To accelerate the I/O performance, Libpubl performs checkpoint on background thread away from the critical path of program execution. And the write function returns immediately after the user buffers is committed via memory fence. While providing background checkpointing, Libpubl also allows application to access user buffers which are still marked as commit states log. When application access the user buffers in commit states, their checkpointing is changed to foreground. We call this early checkpointing. And if the buffers are already in checkpoint process by the background thread, application need to wait until the background checkpointing is done. There are two waiting cases that might increase the application execution times. To minimize such waiting situations for buffer accesses, Libpubl allocates user buffers in Publ type object. We call this Publ object for short. Publ object has multiple preliminary buffers inside, and they are internally assigned as buffers for an application in a circular fashion. Thus, in immediate use of buffer before checkpoint completion will make the Publ object switch to a new preliminary buffer. Libpubl can configure the number of preliminary buffers at its initialization. The table shows the percentage of waiting situations and performance according to the number of preliminary buffers for Publ objects. According to our experiment, the I/O performance saturates around 8 preliminary buffers, so we allocate 8 buffers for Publ objects. To guarantee write atomicity with memory mapped I/O, application needs logging. But if application uses logging, it should write twice in non-volatile area, so there are the performance reduction as shown in logging section of table. Even if only with foreground checkpointing, Libpubl shows the same performance as without logging. Libpubl can further improve the performance by using background checkpointing. Libpubl provides scalability through a fine-grained range log using registry in multi-threaded environment. To avoid too many log equations for a large size access, Libpubl provides various sized log ranging from 4 KB to 2 MB, doubling the log ranges. The figure shows the performance comparison between per-file log and fine-grained range log. With per-file logs, registry searching overhead can be eliminated, but it cannot provide scalability. Only the fine-grained range logs shows a scalable performance on multi-threaded run. There are lists of metadata at the top of each memory file. Libpubl can access the log via the relative offset within the memory file. And Libpubl check whether the recovery operation is needed at every library initialization time. We experimented 4 types of file system in the table. In terms of write atomicity, all file systems guarantee write atomicity in each operation except ext4dex. To evaluate performance, we used 2 types of NVM, NVDIM and Optane. The detail of each system in the slide. The Optane memory is the 2nd generation and only Ubuntu 20.10 or higher versions support its driver. But Ubuntu 20.10 is packaged with the Linux kernel 5.8 and Nova supports the Linux kernel 5.1. So our experiments for Optane system were performed except for Nova. We measured bandwidth performance using FIO. 4 types of file access patterns are used for our experiment: sequential read, sequential write, and random write. We enable refill option for all experiments. If without refill option, FIO fills the data in a buffer once and reuses it repeatedly. Since it is not typical common workflows, we enable refill option. Nova requires frequent kernel mode switches and goes through the kernel IO stack in both read and write. And libnvmio needs to search the registry to read the updated data in read and needs one more additional memory copy for logging than Libpubl in write. On the other hand, it only copies the data in read and exploits user buffers as log in write. So Libpubl shows the best performance. Figure shows the performance of random write with various write sizes. For I/O on smaller than page size, Nova has overhead due to copy on write and frequent kernel mode switches. And libnvmio needs one more memory copy for logging than Libpubl. For I/Os on rather than page size, memory copying dominates as the access size grows. So Libpubl has fewer memory copies, so it performs faster than other file systems. Figure shows the performance of FIO for a shared file in a multi-threaded environment. Libpubl begins checkpointing on background thread immediately whenever logs are available. Libpubl needs a background thread for each IO thread with write permission. For this reason, in the 16-thread experiment, the number of cores is insufficient for NVIDIA system, and some threads may run on the remote node for Optane system. So the performance degrades slightly. The performance of up to 8 threads, Libpubl shows best performance. And Libpubl will scale well in an environment with enough cores for writes. I will conclude my presentation. Libpubl is a library file system that exploits a persistent user buffer as a log to provide low latency, scalable I/O while guaranteeing write atomicity. In our experiments, it gains up to 2 times better throughput, 8 times better scalability compared to state-of-art NVM file system. Thanks for watching my presentation. Thank you.